Hi everyone, back to the word mole. Now, a mole, we already learned, is considered a mass. But a mole can also equal a volume. And we know that a mole can also be defined as a quantity. Today we're going to focus on the definition of a mole in terms of being a quantity. Now, for our purposes, 1 mole in terms of a quantity is known as Avogadro's number. And Avogadro's number is a constant number. It's never going to change. So it's 1 mole is equal to 6.02 times 10 to the 23. Now there's a blank where the units should be because the units are what's really going to change in terms of this definition of a mole. And it's really dependent on the substance that we have. So 1 mole can always be constantly 6.02 times to the 10 to the 23, but now the units are going to be the one that we have to be careful with. So let's take a look. When I look at 1 mole of carbon, the number that I'm going to use is still going to be 6.02 times 10 to the 23 because Avogadro's number is a constant. However, the unit, now I have to pay attention. Because I'm given carbon, the unit for this definition of a mole as a quantity is now going to be atoms. Because carbon are made of atoms. However, now if I change my substance, I now have carbon dioxide. Carbon dioxide is a covalent molecule. So if I said, okay, what's 1 mole of carbon dioxide in terms of a quantity, I'm still going to have Avogadro's number, 6.02 times 10 to the 23. But now watch what happens to the units. Since this is a covalent molecule, my unit now becomes molecules. All right, so let's take a look at other substances that we can encounter. KBr. KBr is an ionic compound, and if I ask for 1 mole of potassium bromide in terms of quantity, it's still 6.02 times 10 to the 23, but now watch what happens to the units. Because this is an ionic compound, I now can either write ion pairs, because it's binary. I can write down formula units. That's something that you might see when we deal with ionic compounds. And we can even just write down ionic compound. That's probably the easiest to remember because you can recognize it as an ionic compound. Now, let's take a look at other things that we can encounter. 1 mole, let's get rid of the S, my grammar's wrong. 1 mole of calcium plus 2 ion. So if I ask for the quantity, it's still 6.02 times 10 to the 23. But because I have an ion, I now write down the unit of ion. I could also write down particles. You could possibly see that as well. It's a charged particle, so we can use that as the unit. Now, the last example that I have for you is a diatomic element. It's different from carbon because carbon is monatomic element. So the quantity is still going to be 6.02 times 10 to the 23. But you have to be careful. Remember that diatomic elements are still held together by a covalent bond. So for this one, we would write 6.02 times 10 to the 23 molecules. All right, so be careful. When I ask for a mole in terms of quantity, the number 6.02 times 10 to the 23 will always be the same exact number over and over and over again. But the units are very specific. Now, there are a couple of things that I have to go over with you before I show you how to convert from moles to quantity or quantity to moles. So the first thing I want to go over is really scientific notation and the use of exponents. When we put anything into scientific notation, you should remember that the form is always the same. The form is always a base times a power of 10 to a very specific exponent. I want to remind you specifically about the base. The base of any scientific notation that you're going to write should always be greater than 1, but less than 10. So the example that I have for you here is wrong in terms of how we write scientific notation correctly, because the base is not greater than 1. Well, it is greater than 1, but it's not less than 10. So it doesn't fit the format. So the deal with the base is I now need to move the decimal, the imaginary decimal that sits at the end, in order to make it fit my form. So if I have this imaginary decimal, as I move the decimal either left or right, the exponent is going to change. Now, in terms of this, if I want a bigger base, what you're going to have to do is you're going to move the exponent to the right, move the decimal to the right, but you're going to see that your exponent will get smaller. Now, if I want a smaller base, like in my example here, I'm going to have to move the decimal to the left-hand side, but I'm going to see that the exponent that I use is going to be larger. All right, so let's take a look at the example I'm given. 507 times 10 to the 23. This imaginary decimal right here after the 7, I need to move to the left because I want a base that's greater than 1 but less than 10. So I'm going to have to move this decimal 2 times. So I end up getting a base of 5.07. Now, since I moved my decimal to the left 2 times, that means that my exponent must now become larger by 2. So instead of being 5.07 times 10 to the 23, it now becomes 5.07 times 10 to the 25. So the number of places that I had to move the decimal is the number of places or changes that I'm going to change in my exponent. So this is now appropriately written in the correct scientific notation. It is not acceptable to write scientific notation like I had in the example. 507 is a base that's much too large. So you have to change that base number to fit the format for scientific notation. And if you change the base and move the decimal around, then you have to change the exponent. So that's my first hint. My next hint is really dividing numbers with a power of 10. Now, some of you have learned this, some of you have forgotten this, but I just want to show you an easy way to do this, even if you don't have a graphing calculator. Now, when I divide the numbers, that's perfectly fine. I can divide the bases. 8 divided by 4 is simple. That's going to be just the number of 2. Now, the exponents is where I'm going to have my issue. Some of you know that when you divide 10 to the 25th over 10 to the 23, you're going to actually subtract your exponents. So this ends up becoming, when I subtract the exponent of 25 from 23, now really just 10 to the second power, right? So whenever you're going to divide by a power of 10, all we have to do is subtract the exponents. Now, when we do the different order of operation, different, what's the word I'm looking for? When we have to multiply numbers with the power of 10, it's going to be slightly different. In this case, what I'm going to have to do is I'm going to have to multiply first. So I can multiply the base numbers. 8 times 4 ends up being really just the number 32. That part's easy. But now it's the powers of 10 that I have to watch. When I have to multiply the powers of 10, what I'm going to do is I'm going to add my exponents. I have to add those together. So this becomes 32 times 10, and 25 plus 23 ends up becoming an exponent of 48. So when I multiply these two numbers together, I now get 32 times 10 to the 48. Now, this is still wrong, just to remind you, because it's not written in proper scientific notation. So I would have to change this number, or the base number, into a number that's less than 10. So this imaginary decimal that sits here has to move one place to the left. My base number ends up becoming, 3.2 times 10 to the. Now, since I made my base number smaller, my exponent must now get bigger. So it becomes times 10 to the 49. It goes up by one number because I moved the decimal to the left by one number. All right, so that's just some things to remember as we learn to convert from moles to a quantity and quantity to a moles. Now I'm going to show you two sample problems. I'm going to show you two different methods, just like I did before, and you do whatever is comfortable for you. So sample problem D, it reads how many molecules are in 67.2 moles of H2S. Now I'm going to use dimension analysis, and the first thing I'm going to do is I'm just going to set up my dimension analysis T, this little chart that I'm going to use. Specifically because I don't need to find molar mass, because this is not the definition of a mole in terms of mass. This is just quantity. I'm going to take what I'm given, which is 67.2 moles, and I'm going to put it on the left side of the T. On the right side, I'm going to use my definition of a mole, or the definition of 1 mole, in terms of quantity. So this really becomes 1 mole is equivalent to 6.02 times 10 to the 23. And they actually give me the units, which is great. But just in case you wanted to know, H2S is covalent. So since it's a covalent, I'm going to write down molecules here. And you have to write your units. Some of you are not setting up your problems with your units. Now, by setting it up in this manner, I'm able to multiply across and then divide going down. And the easy part of this is that the moles cancels themselves out, and I'm left with the unit that I want. Now, I can easily put this into any calculator. You do not need a graphing calculator. We just multiply 67.2 times 6.02. That ends up being just 405, and then I'm just going to take the power of 10 with me. Now, this answer is not correct because the scientific notation is not in the proper format. So just like before, I need to make my base number less than 10. Now, by making my base number less than 10, I need to make it smaller. So this imaginary decimal that sits at the end of the number needs to move to the left 2 times. So my new base number becomes 4.05. Now, since I make my base smaller, my exponent must now get bigger. And it's going to get bigger by 2 numbers. So this doesn't end up as 10 to the 23, but it should be 10 to the 25. I'm going to write my units, so it's wrong without a unit as well. And then that's my answer. That's how many molecules are in 67.2 moles of H2S. All right, so that's how we would do it in dimension analysis. Now let's try a different problem using proportions, which some of you are much more familiar with, but do whatever is comfortable. So sample problem E, it says how many moles are in 2.41 times 10 to the 23 atoms of Na. So since I'm going to set up my proportion, all I have to do is take a look of take a look at what I'm given and remember that 1 mole is equivalent to 6.02 times 10 to the 23. And in this case, I'm given sodium and also the word atoms. So I'm going to write atoms here. Now, all I'm going to do right now is just set up my proportion. Once I know that 1 mole is equivalent to 6.02 times 10 to the 23 atoms, then I have to figure out how many moles are actually in 2.41 times 10 to the 23 atoms. Since it's a proportion, I'm going to cross multiply. Let's just make it more clear. I'm going to put the equal sign in the middle. And this was erased, so let's fix that. And then I'm going to cross multiply. When you put the numbers in correctly, all right, and you divide your exponents and you divide your numbers, you end up getting the number of 0.40033. Now, I need to put it in the correct number of significant figures. The digit that I have in front of me is in 3 sig figs. So this number that I end up getting also must be in 3 sig figs. So I start counting from the left. The first significant figure is the number 4. The 0 doesn't count. This 0 counts, and then that becomes my helper number. I end up, as my answer, 0.400, and then I end up with the unit of a mole, or moles. So when I have that many atoms of sodium, it's only equal to 0.400 moles. Okay? Don't forget to cross multiply when you're doing proportions. All right, and don't forget to write your units in the proportion and also your units at the end. Okay, that's it for now. You're going to try some on your own, and I'll see you in the next lesson.